talk on the vaccination. We got some HR years of the data. Already in the or I think the project was very one yeah, so she's going to talk on this aspect of monitoring vaccination before see how
I'm still connected though.
yeah, but maybe you need to check. Let me see control. But we need to change this. Oh, okay, another one. All right, so thank you very much for final talk. Who's going to talk on deep data driven economies of malaria vaccination? So please go ahead.
Okay, so I'll be checking on the big data driven models, given the analysis for malaria vaccination model, and because supervised by Dr. Senegal. So to move in, this is the outline of our introduction, the aims and objectives, the methods that was used for the research, then our mathematical analysis for malaria vaccination model. And also we went into our deep data driven analysis, finally to our conclusion and recommendation. So earlier, our PhD students and our supervisors and lecturers are already spoken about how malaria is a health concern in the world and as well as sub-Saharan African regions, and also has led to the death of most people. So with this concern, the World Health Organization, together with the Alliance, introduced a malaria vaccine known as the RTS vaccine, mostly known as the mosquito vaccine. And it's not being used everywhere in Ghana, which is Ghanaian and RTS vaccine. So although the vaccine is not 100%, they're able to reduce infant mortality by 30%. So with the help of the data models like the SR models, the SROP models, SDR models, we also have our agent-based models, also known as the LBMS, and then the machine learning model that will be used in my work. Use to help us analyze trends and also manage disease and population dynamics. All right, so we also went ahead to do the aims and objectives. With the aims, the main aim objective was to develop models optimized vaccination strategies. We also went ahead to analyze the forecast vaccination impact, understand population dynamics in vaccination, and optimize strategies to reduce infant mortality rates. All right, so we then went ahead to the data-driven neural networks. Now, first, we need to understand what a data-driven the models, we have our neural networks. For the neural networks, we have our residual neural network that is being simply as our ResNet. Then we have the long short-term memory known as the LSTM given here. I have a bidirectional long short-term memories, an upgraded version of the LSTM, which trains the data from both directions, the front and backward direction. That's the BiLSTM. They also have a gated current unit seen here as well. And as well, the mathematical model that we use for simulation was the SIR model. So my focus was on the RSTM vaccine. So we studied and tried to formulate a mathematical model that led us to a seven compartment model, where our S denotes the statistical population, the I denotes the infectious population, the R is the recovery population, the V1, V2, V3 is the vaccination population at different stages. So you can see the parameters that show the transmission from one compartment to another. So our lambda is our birth rate, our alpha given there is our infection rate, the beta is the recovery rate, the delta also is the death-induced rate for infection, and the gamma is the loss of recovery. So just to explain that, the rest is going to describe the table here. All right. So moving ahead, based on the model that was formulated, we are able to derive a system of ordinary differential equations to explain our given model. Okay. So moving ahead to the qualitative analysis aspect of the model. So we tested for the boundedness and positivity of the model. And then there's a theorem that for the boundedness that says that all the solutions of our model is bounded in the physical region outside. And from our computation, we realized that it is only possible if the total population of infants is greater than or equal to 0 or less than or equal to the ratio of the birth rates to the death rate. And then for the positivity theorem, it says all the solutions to our model has to be positive. So based on our computation, it's also for we only wrote for the statistical compartment, and we derived that when our time is greater than 0, when we consider our initial conditions, all the solutions we will get would be positive in that instance. Then we went ahead to find the sphere equilibrium. So when we say this sphere equilibrium point, is the point being the population dynamics where there is no infection in the population. So when there is no infection in the population, meaning that there is no recovery. So if that's being said, to attain our sphere equilibrium point, we equate all our systems of equations 0, and then we found we make the compartment the subject so that we can find our equilibrium point. So because here it is being seen, this is our equilibrium point of this book S. Equilibrium point for I, when we say this means the 0, so 0, 0, and V1, V2, V3, V4 is being displayed here. Now, for the basic reproductive number, the basic reproductive number is crucial in helping us determine whether the disease will fade away from the system or it will persist for a very long period of time. So with this, we use our next generation matrix. And then for the next generation matrix formula, we consider only the infectious compartment. So when the F from this side indicates the new introduction of infection into the infectious population, and the VI determines the rate at which individuals see the infectious compartment to another population. So based on our computation, we had this as our R0. And then there are remarks or conditions that if our R0 less than 1, meaning that the disease will fade from the system or the population. But if our R0 is equal to 1, meaning the disease is stable within the system. So it's that will increase or that will decrease. But if R0 is greater than 1, then it tells us that the disease will persist in the system for a very long time. So we then followed on to the local stability and speed points. To attain the local stability and points, we use the Jacobian matrix. And then the theorem here says that the system is considered locally and statistically stable if the eigenvalues of the Jacobian matrix are negative, are all negative. So meaning when you do your computation of your Jacobian matrix and you put in your distributed equilibrium points to attain your eigenvalues, all your values have to be negative. But from my computation here, you realize that our lambda 2 is positive. So to make it negative, our lambda 2 has to be less than 0. So from further evaluation, we have taken this, meaning now the system is locally and statistically stable. If it has been achieved here. Then we also went for the global state, meaning we did an entire population, trying to find out the situations where we fail away within the entire population. And then in this case, we didn't use the Jacobian matrix, we used the Lacuna function. And then the Lacuna function allows us to use scalar functions to meet this kind of condition. So with the Lacuna function, I decided to choose my infectious compartment as my scalar function. Then I did a derivation of it where I'm able to identify the arrows within my derivative Lacuna function. And I use the condition that says that if the Lacuna function, the derivative of it is less than or equal to 0, then I'm able to achieve my global stability. So from here, if I'm saying that my infectious population is never negative, because in the normal sense, biological reasonable sense, we don't have a negative population. So in the infections here, it will be positive. So if this is positive, this rate 2 don't have negative value. So our rate 2 automatically is positive. So meaning we are going to only consider the R0 minus 1 here. So for the R0 minus 1 here, it has to attain a global stability when the unit is less than 0. We are able to get R0 is less than 1. Hence, the disease has failed from the system. We are able to achieve that. Now, to attain the trivial case, if we make our R0 equal to 1, meaning these 4 equations for our derivative Lacuna function goes to 0. Yeah, so at the end of the day, within a global or the entire population, the disease will be able to take it away. Okay, so now we went ahead to the sensitivity analysis. So the sensitivity analysis helps us to determine the parameter that contributes to the spread of the disease in the population system. So with the help of this, we use the partial round conservation coefficient to help us attain that. And with this graph that is speaking, at the positive region, you see bars here, and at the negative regions, you also see in the bar. But R is helping us identify the parameters that contribute to the spread of the disease. So an increase for the positive side, an increase in those parameters indicates that the disease will spread within the system. And then a decrease in those parameters will indicate that there will be a decrease in the spread of the disease within the system. But for the negative side, if the bar increases, it means that the disease will reduce within the system. It contributes to less spread of the disease in the system. But if the bar is less, if there's a decrease in those parameters, the spread of the disease within the system will be much more, because they contribute much more to the disease spread within the population. Now we went ahead to do our numerical simulation. So for numerical simulation, since we're not able to attain actual initial values, we estimated the initial values for the successful, the infections, and then the recovery. But for the vaccination 1, 2, 3, or 4, fortunately, we're able to attain it from the malaria vaccination implementation plan for Ghana. So we incorporated that into our simulation and had this projections here. And then compared initial stages, the infection within the population was very high. But just when individuals started to get vaccinated, the infection and then the recovery also increased. But because a lot of people who get vaccinated, the population was very less. We are unable to see the vaccination population from this distance here. Hence, I have to separate it here. So I'm seeing the trend of the vaccination population. Okay, so moving on to the neural network aspect. Since we had challenge in getting raw data for our neural network, we have to use a generated data. and we fed it into our neural network that I set up there. And the neural network remained trained against the parameters and was able to produce its own parameters. And the parameters that were produced were either slightly the same as the actual parameters. Some few changes, probably like 001. Because here we have 0.2, that's 0.29. That is closely related. Okay, so for the vaccination impact, so now we decided to find how vaccination impacts in the population dynamics. Sorry. So at a constant rate of each 4 vaccination, said okay. So test for how vaccination affects will cause the disease to spread or the disease to die of the population. So we tested for when the efficacy of the vaccine is 0.7. And also when the vaccination is sponsored, realized that we played around with, we took random values of our alpha and beta. So with the random value of our alpha and beta, when the vaccination rate is 0%, and alpha is 0%, and beta is 0.15, realize that our alpha is greater than 1, meaning in this instance, the disease would spread so much to be there for a very long time. But when we round through and realize that when the vaccination rate is 10% at these 4 stages, the R0 is less than 1. So meaning the disease fades away in this instance. But when we take at this side of the table, when the efficacy of the vaccine is 0.94%, and then the vaccination rate is still constant at 0%, the R0 is still more than 1, meaning the disease will still persist in the population. But when the vaccination rate is 20%, the R0 is much closer to 0, meaning that this will fade much faster. And then in this instance, realize that this one is what less than 0, so less than 1, less than 1. But if you check the values here, this one is much away. This is because when we look at the alpha beta here, this one, the alpha is less, and then the beta is more. Meaning our recovery rate is much more than those who get infected in the population. But this one, you're realizing that our infected rate is higher than that of the recovery rate. So you realize that in conclusion, we are able to identify that when there's an increase in vaccination rates at all 4 stages, and then there's an increase in recovery rate and then length of the infection rate, then the possibility of the chances of the disease fading away from the system is very high. All right. So now we did a comparison here between the actual simulation and the neural networks. So based on the values, the learned values of the neural networks and then the actual values that we use for our first simulation, realize that we're able to get this back to the same thing. Meaning our neural network is able to predict the exact population just like our actual simulation does. Okay, so the vaccination graph here. Now we went ahead to do our simulations when the vaccination rate is constant at 0.7%. And then in this instance, realize that the infection rate population is 0.5. It's not really visible here, but it's 0.59 or almost 0.6%. But when there's no vaccination in the population, realize that the infectious population increases very high to almost 0.9%. We also tested for different ways when the efficacy of the vaccine is different, it's not constant. And then also when the vaccination rate is constant and when the vaccination rate also varies at certain stages. So this time when the efficacy of the drug increases at each vaccination stage, and then the vaccination rate is constant, we realize that the percentage of infectious population is 0.27% there. And then this side, when the efficacy of the drug increases at each stage, but the vaccination rate decreases at every 4 stages, at each stage. realize the infectious population increases much higher, 0.28%. Okay, so now we also try to see how the neural networks can be able to predict the daily infectious cases. That's actual cases that have been recorded. So for the residual neural network, that are ResNet, so able to predict actually our daily infectious cases. But when it comes to the BiLSTM, the neural network that was able to predict much more was our BiLSTM. Yes, our BiLSTM was able to predict much more about daily infectious cases. Okay, now we came on to the error matrix, where we are able to view the performance of each model based on their root mean square error and then the mean absolute percentage error, as well as the evaluated variance. That's from the next page. And for the neural network that is able to produce the least mean square error and the mean absolute percentage error, from the chart here is our BiLSTM. It's very short here, so meaning the best model for our neural network in predicting our daily cases is our LSTM. Now for the evaluated variance, it's different. For that one, the neural network to produce the highest evaluated explained variance, explained variance is our BiLSTM. So in general, you're able to tell that from the neural network that was able to give us high prediction of the cases, our BiLSTM. All right. So finally, I would say that based on this research, we're able to develop a mathematical model of the experience of malaria vaccine, and then that lets us know the impact it had on eradicating the malaria disease from infants, and also we also perform malaria vaccination that have identified parameters that affects the spread of the malaria. And then because we're not able to use real data for our simulations, so probably the performance of each model that we have is telling us that is our BiLSTM. Supposedly we had actual data to work on our model. Probably the best model or the best neural network that would have attained might not be BiLSTM and other models. Thank you very much. For this instance, we took random values for our form success cases where we had to know whether the disease works. Yes, and we know strategies on how to improve the malaria vaccine.
Random values.
Yeah, I agree with you actually. That's we also tried the instance where probably if the first of the vaccine is 0.7, give it a rate like just show that let's try for one efficacy of the vaccine, right? And at least it is, yes. And then try the alpha beta and run it on to find out instances where the disease fade away from the system. That's when we're able to identify that even when the vaccine is 0.7, and then our infections rate is still high. Even if the disease will fade away, it will not fade away much faster. Yes, as compared to instances where we are getting high rates of recoveries, and then the rate of which people are getting vaccinated in the population is much higher. Yes, and then the efficacy of the vaccine is also effective, like it's much higher to sustain infants for a very period of time. So that means that within that population, a lot of infants that will die from the malaria disease, very okay. Yeah.
We also show the some
Yeah.
they were not performed.
Yeah.
So how to explain this? And can you show us that the simulation study is simulate practice once the end of pretty close. What do you use to train the use cases or just
No. Okay, so to train them, what they have to do, so that they just generate data. It's a generated data that will affect to the humanity. By this and then,
like loss function, say some
yes,
early output is
yes,
the
the actual, yes, the daily content, yes.
because have you seen the France who was the research for this problem?
Actually,
Was
yeah, so it wasn't all the neural network that was trained in the just the layered files. So it's just one neural network. Yes, it's not all. If it's different, we have had different tables that yes. The yeah, we feed the model with our actual values and into the neural network, so that it trains and learn the values to give us estimated values. Shared parameter for the I can't really recall the number of experts. These are permitted values. Yes. Yes, actually, this is quite limited. That's the reason why we're running and investing the answer. We have to change it. And that also affects the reason why we were doing the sheets, able to predict the daily cases. So it's based on the examples. Or we will be able to find the actual the insight.
concerned about the problem with the sense you should work out on that.
Okay, so we are considering and more than at one time is what is the S of T also, the result I will get, the X of T will be that better than what share one. Yes, so we want to find a situation where we are going much about the initial.
Very hard to long run.
Yeah, I'll consider that.
Okay, yeah. If not, happy to always. I'm more happy with how we can manage and share stuff. Thank you all for coming and yeah, the feedback.